puzzle for today, 354. Is a combinatorial logic problem. And here's the URL. And here's the text. Oh, no, this is the wrong one. BBC 354, this is the correct one. I can make it a little bit smaller. Here's the link. Doesn't get into an embed frame. So we also want to try and extend this puzzle and generalize it. So let's define some variables. The number of people is 7. And each one orders a different dish. We don't care what the dishes are. The only thing that we need to know is who ordered it. So the dish labels will simply be the index of the people sitting at the table. So dish 0 will be the dish that person 0 ordered, and dish 1 will be the dish that person 1 ordered. So in this case, an order would be represented as simply the first person ordered dish 0, second person ordered dish 1, 2, 3, 4, 5, 6, so on and so forth. So what the waiter is supposed to do is he's supposed to bring this 0, 1, 2, 3, 4, 5, 6. But he messes up. So we want to make we now have to see all possible ways that the waiter can mess up the order. So here's the order that the waiter got. And then he will return the not the right order. Right? Now, that means, since it says nobody gets the correct dish, that means that for the first dish, there's 6 possibilities. 1, 2, 3, 4, 5, 6. Right? And for the next dish, there is also 6 possibilities, but one of them will be taken by the first one. And for the second dish, let's say in a third dish, there's also 6 possibilities, except the ones that were already taken by customer 1 and 2. So that means we need to calculate the possible ways then that the waiter can return the order. Now, and I want to be able to do this for any number of people, not just for not just for 7 people only, because eventually we want to extend it. So I need to pass in the current index that we're dealing with. We start with 0. And in customers, so that'd be 7 at the beginning. Yeah, maybe I don't need all of these. Let's check. So we pick one of the dishes off the order and I iterate through all of them. Right? Now, if the order is equal to the current index, which means the index of the customer, then that's not allowed. So that order has to be different from the current index. And let's see. I need to also know the index of the order that I'm using. Then I check what the waiter will bring. OI plus order OI plus 1 to the end of the list. So what we have now is a recursive algorithm, O plus R for R in rem. So this is a recursive algorithm because to calculate weighted brings, I call weighted brings itself. But with a shorter list. Maybe no orders if the list is empty. So if order is not none, I think this will just skip through anyway. So now let's see if this works. Now to debug a recursive algorithm, it is actually quite helpful because you're calling the same function over and over again to have a sort of level variable that allows you to help and trace the execution of the algorithm. So level. That's what we're calling. And that will return this value. So now let's try this out. So I'm going to make small set of orders, just 2, 0 and 1. and then see what the waiter actually brings. So that will be order. Current index 0 and level 0. IO, not OI. O index, O index, O index. So we want to bring the waiter as orders 0 and 1. Now for the first customer it cannot put 0 there, right? Because that's what they actually ordered. So there's only 1. So for the next customer it has to give a 0, then it calls 2 and then it returns the empty list, and the empty list, that's incorrect. So why if O, then it calls this, then return O plus R for R in the remainder. And I think that means needs to be a list of lists, so I think I need to return a list of an empty list. And then it works. So the waiter brings 0, 1. Orders are 0, 1. Then the only option that he has for returning is 1 and 0. Right? Because 0, 1 would be correct order for 2 of them. So then we can try 0, 1 and 2. Now we have more possibilities, but it only returns 2, 0, 1. Oh. Return dot extend. Too many empty lists. So let's have a look here and see what we're actually extending. Here's the remainder that we're getting. Way to brings, way to brings. We don't get any. Oh, that's because when I pass in the last level, then I will get a empty list to come back. So the remaining order is this. Or I need to call this all the time here. Still no results. 0 to 1 receives an empty list, empty list, empty list, empty list. How come? Yes, so I need to check so if it's then that's possible. Otherwise the remaining order is this. If the length of the remaining order is greater than 0, so there's still something to process, then I want to call this, if this returns an answer, then that's correct here. Else I simply append a list with O to my returns. Reader brings comma. reference before assignment. So where's the otherwise if remainder, then that should be there. No, it should be there. Yeah, no remainder there. So now for dishes 0, 1, 2, then we can do 1, 2, 0 or 2, 0, 1. Two possible orderings of the dishes in such a way that nobody gets the correct dish. So this could be a 1 or a 2. This can be a 0 or a 2. So if this is a 1 or a 2, then it must be 2, 0. And the last one has to be either 0 or a 1. 0 or a 1. So how about 1, 0? Then I would have 2, so that doesn't work. 0 is not possible, so I can have 1, 0, then I would have a 2, that's not correct, so I can have 1, 2, then there's only a 0 left. Or I can have a 2, then I can have a 1 there, that would be incorrect, or 2, 0, 1. So this is now a function that generates all the possible orderings that the waiter brings. Now I'm gonna turn off the print statements that we used for debugging. Actually, it would be more professional to use the logging subsystem in Python, which is also very powerful. So you may want to have a look at that. So now our orders are number of people at the table. What the waiter brings is this. I think I have to convert that to a list. attribute list, toList. So the number of orderings, number of permutations grow with n factorial, right? So so they grow very quickly. That's why I took off the print statement, and you can see many different orderings already. I need to import math. So out of the 5,040 possible permutations for a list with 7 entries, 1,854 have the property so that not a single dish is in the correct place. So now one thing that we can do in order to improve this is that instead of doing a return, I can use a generator, because the problem is the list grows very quickly, so I will use a lot of memory, but really I only need to process one entry at a time. So we will use what's called a generator, which is sort of a restartable subroutine. Instead of returning, we're yielding a result. And then if I iterate over this, I can just pick out one element at a time. Now this will not work anymore because a generator doesn't have any length argument. So I need to convert it into a list. The waiter generator. How come it just says 1? Oops. Turn. See what happens when I add the print statements there now. And of course not so many. Let's just do 2 people. weird. That should actually call something. I guess it doesn't work so well with the recursion. Okay, so no, I don't get any call. Like at least the first one. Ah, because I don't actually access them. Yes, so now we get the now my list is slightly off. So WS is equal to W for W in WG. And that's a list with only a single entry in it, which has all the solutions. That's why it comes back as one. So the problem is 0, 2, 2, 2, 2 returns none. See the result. We don't need to so it brings this which is the generator now. And then it will always call that. So be a list of O plus R, a list of lists. So in this case, I think the generator is not really that helpful. If I want to use the generator here, then this would be the generator. So then the list is this, R for R in RG. And then if we have an element, still get too many. 0, 2, 2 returns 0. 0, 2, 2 returns 0. So waiter brings 0, 2 receives this result. So that's one too many lists now. So that yields a list. Okay, so that actually works now. 120, 201 are the two solutions for 3. And it's because the generator sort of put in an extra list here. And since it's a generator, I cannot test if it's null or not. Yep. But that works now. It's actually not so efficient now because we will actually collect the list all the way up to level n-1. So the amount of memory that we save is not as efficient. We still save a little bit of memory, but not as much as in some other cases. So here, let's now comment those out. And this would be people from 0 to 7 people on the table. Oh, and then I don't want to print it out. I just need to know the length of it. 1. Why 1? More lists. $1,854. So that's the same answer as before, except now we use slightly less memory, and I can iterate through them using the generator here that is returned by what the waiter actually brings. So now we need to check if the orders can be rotated, right? When I rotate the table, then I can check, first of all, if there's always at least 2 dishes that are in the correct order. So I have another, actually let me print this here. So I define a function that checks the order the minimum number correct given what the waiter returned and what was actually ordered. So then it's a Chinese table. So what I can do is I can rotate it around. Now there's that many people, that many positions. I can basically rotate by this many. minimum number of correct dishes is +1. So this one is impossible, right? Because there's 7 people and now 8 orders are correct, so that will never be. That's just a dummy value to check, to make sure that the min update is going to work correctly. So now I need to compare shifting all the orders by I to what was actually ordered. So that means for J in range order, then I have to calculate how many are correct. So right now zeros are correct. Then if W of I plus J modulo and the number of people is the length of the order, this would be MP. This would be MP, and yes, NP here too. So the actual order so if I have I plus J modulo MP if that is equal to I, then correct is equal to correct plus 1. If correct is less than the minimum correct, then the minimum correct is how many I have correct now. Notate it out. I can also update the max correct. Number of correct dishes, and then return min correct and max correct. W, if it's not rotated, then they would all have to be correct, which means Um, and that's here, and that has to go there. So now let's try that out. Print, check. So this is now check min max correct. Always important to have the right name for your functions. W in order. So I don't want to do too many, so we'll just do 3 for now. If order is this, order. This will be just in one here. No, this one will be MP. This here should really be just one because I just come from 0. Yep. So y MP is the length order. Print I J NP. Print W, I think. Doesn't actually print. Oh, here. 120 201. So that's because the generator, I guess, always returns a list there. So the minimum number of corrects is 1 and the maximum number of corrects is 2. That sort of makes sense, right? Because if I had 3 correct, then at least one of them would be in the correct position when I generate the orders. So now we need to calculate all minimum and all maximum, and that would be the length of the order plus 1 and minus 1. If our min is less than all min is equal to our min. If our max is greater than all max, then all max is equal to our max. And then let's print them out. Our min, all min. All max. So now our min and all max is going to return the same, and I just need to change this to 7 now, but I want to turn off all the print statements. So here, get rid of this and get rid of this. So for 7 now, it also returns 1. One 0 3 2 5 6 4 0 1 2 3 4 5 6 returns 1. It only checks 1 though. so there's a problem with the generator. I'm just gonna return this one here and not have the 0 index. So this is this is this. Okay. Int object, that's because to get rid of this. So 1, 2, and 0 has minimum 1, maximum 1. 2, 0, 1 has minimum 1, maximum 1, correct? That's not right, because 2, 0, 1 I could rotate so that it is 0, 1, 2. And similarly for 0, 0, 1, 2. So the rotation doesn't work there. Our check. So WI J. Now I want to rotate. It's probably better J plus I. Now that's my order, so WI that shouldn't be J, that shouldn't be I, that should be J. Because dish 0 should be dish 0, so the question is if the entry at that index plus the offset is equal to dish 0. Zero? Is it possible to get 0 here? 0, 1, 2. Maximum is 3, that's correct now. If I rotate this to 1, 2, and 0, one more, then I get 0, 1, 2, then all of them are incorrect. Here I have 2, 0, 1. If I leave it like that, then they're all incorrect. So that would be 0 if I don't rotate it at all. But then that's not what they're asking here. with any any rotation. So if I do the first rotation, then I get this many correct. If that's less than what I have, then that would be the minimum number correct. Yes. But 201 the best I can do is rotate it. So I'm looking at the all max here, so I can get 3 correct. That's the best. So here I can rotate it, I'll get our max. And then I need to look for the minimum of the R maxes. So all minimum is the length of the order. If R max is less than the current minimum, then I remember it. And this part here doesn't really make sense. R max int and tuple. Oh. So in this case, whatever the waiter brings, I'll always be able to get at all 3 dishes correct. So for 3, that's correct. For 7, oh. Big printout. No printout here. All min x. So here this now proves the answer by the BBC, right? At a minimum, whatever the waiter brings, for 7 people, there will always be 2 people that will have the correct dish in front of them. You can actually prove this analytically by sort of the pigeonhole principle, right? Because if I rotate the table, then at least one I can always rotate it so that they will have the correct dish in front of them. So then there are 6 positions open, and for the 6 positions there's 6 slots. But if the first one of the remaining ones is not in the correct position and the second one is not, there's only 6 possible choices for where to put the non-correct dishes. So one of them must be at least guaranteed to be in the correct position. So that's proof by pigeonhole principle, I think it's called, where you simply show that there's no other option left anymore. One of them has to be in the correct position. Let's say we have 3, then I rotate the table so that I have 1 in the correct one. Then now there's 2 missing, right? 2 that I can still align. Now the first one cannot be in the right place, but then the second one also. So for 3 it doesn't work. No. So how do I used to remember how to prove that, and the idea was that there's just so many that you can put in the wrong position before you're guaranteed that you have to put one in the right place. So we have 6, we fix 1, then we have 6 left for a table of 7, and 6 slots. So how did that go? Because for 1 dish, but now I'm allowed to rotate the table more, right? So if I have a possibility that by rotating the table 7 times, at least one of them will have their own dish in one of the other 6 rotations of the table. So because there's 7 possible positions that I can rotate the table to, but only 6 that are not in the correct position, not in the correct place. So that means there must be at least 2 diners that have the correct table, the correct dish in front of them. It's not for a single draw, but it's when I rotate the table around. Because at the beginning it said that all of them are in the wrong position, right? So initially when the orders come, none of them are in the correct position. So then I rotate the table. So now I can rotate the table with 7 possibilities, but there's only 6 wrong dishes. So each diner is going to have 7 dishes move through them or rotate in front of them, but only 6 of them can be the wrong one. So 7 is larger than 6, so there must be at least 2 that actually have the correct dish at one rotation of the table, not by just bringing the order, but also by being able to rotate the dishes. So this is a pretty fun puzzle. We can then extend it. For example, we could calculate the average number of correct dishes, or the maximum number of correct dishes, or what happens if we increase the number of people. So if we go to 8, then the proof still works. And I can increase the number of people on the table. Usually in Taiwan we have 10 or 12 people on a table, I think. But now you can see the algorithm also runs a lot slower because the number of permutation grows very quickly. And we're using quite a bit of memory. If you check, Google is not so happy with me right now. But that will be the solution for the Chinese diners problem from the BBC. Now let's move on and finish off the Dennewitt-Hartenberg convention. Just a little bit left, and then we're done for this weekend. because we haven't discussed the assignment of the coordinate frames. So for the rest of the frame assignment, we have three cases to consider. Zi minus 1 and Zi are not coplanar, so they don't lie within one plane. Zi minus 1 and Zi intersect, or they are parallel to each other. Oops, too many lists here. So first one is, if they're not coplanar, then the x-axis has to be the one that connects Zi minus 1 to Zi, right? So it must be on the shortest line between Zi minus 1 and Zi. Since they're not coplanar, that means it looks like this, right? They're not lying in one plane, they are like that. In that case, the shortest line is like that, from Zi minus 1 to Zi. That has to be xi then. And then wherever xi and Zi meets, that's the origin of the coordinate system OI. And then we just have to assign yi to make sure that it's a right-handed coordinate system. So xi must be because it must be parallel to, must be perpendicular to both of them, right? Xi by Denavit-Hartenberg convention is perpendicular to Zi minus 1, and it's part of the OI coordinate system, so it must also be perpendicular to its Z coordinate. So that gives you then the shortest line between Zi minus 1 and zi. Origin OI will be at intersection of xi and zi, assign yi to make it a right-handed coordinate system. So if zi and zi minus 1 and zi are not coplanar, then we have no choice. There's only one possible location for OI. Now, if zi minus 1 and zi intersect, then the situation is a little bit, or is similar. Actually, xi must be the normal passing through the plane spanned by zi minus 1 and zi, and going through the point of intersection of zi minus 1 and zi. So now that means we also know where the origin is of OI. Because that must be at the intersection. Assign yi to make it a right-handed coordinate system. And that now means that alpha I, which is the angle that we need to rotate around x to align the new, oh no, there's nothing else we need to say there. So now if zi minus 1 and zi are parallel to each other, then all lines, all normals to both of them will have the same length. So I can choose an xi anywhere along zi and perpendicular to it. So we usually align, then we can align xi so that di, the displacement, is 0, and also in this case alpha I will be 0 since the z-axis I minus 1 and zi are parallel to each other. So that's this case. The two z coordinates are parallel to each other. I can move x then anywhere I want along here. So we move it so that di is 0. Also, alpha is the twist along x to align the new coordinate system, the new z coordinate system. However, in this case it will be 0 because if I translate along x, then the z coordinate is going to be already pointing in the right direction. There's no more rotation along x that I need to apply in this case. So now, after you establish your frames, then you get the set of link coordinates, including your link length, link twist, and the joint angle. And what did we call A though? A is the link length, link offset D, that's what I meant. So joint angle theta, you will then have joint angle theta link offset D, link length A, and link twist alpha. So after you assign the frames, you get the coordinates. You have your 4 numbers, and then you can calculate the transformation matrix. So first you assign the z-axis to your robot such that the z-axis is your axis of actuation. You can then start assigning the frames in such a way that if you follow zi minus 1, it will intersect xi. Then you can follow xi and you will be at the next joint, at the next yeah, joint at the next coordinate system, coordinate frame in your robot. We assign X and Z here usually. So the Y coordinate is just used to make it a right-handed coordinate system. So Y, we don't really have any choice. Then we make this DH table, which is a set of parameters that we use. And the meaning of the various parameters is given here. Joint angle, link offset, link length. And link twist. Once you have the table, you can calculate the homogeneous transformation matrices. And then for forward kinematics, you just need to calculate the compound transformations with the variables. Now for forward kinematics, we're interested in going from the inertial frame, frame 0, to frame n. Now A1 will be a function of theta 1 if we're dealing with humanoid robots with revolute joints, and this will be a function of theta n. Then this transformation matrix, if you plug in value 0, 0, 0, it will give you the position of the end effector of that kinematic chain in the world coordinate frame. And that's it for today. We finished forward kinematics and the Denavit-Hartenberg convention and algorithm. And next class we will start looking at the inverse kinematics, which are they're the more difficult but also the more useful problem. What you can do now is, if I give you the joint angles, 10 degrees, 12 degrees, 19 degrees, then you can tell me where the finger of the robot is pointing to, or what the leg of the robot is going to be. But you cannot, we'll look into the problem, the inverse problem, saying I want the finger to point to here. What joint angles do I need to send? That's known as the inverse kinematic problem. That's sort of what we need if your robot needs to be able to pick up an object, right? Then it knows where the object is. It needs to move the hand to be able to pick it up correctly. In order to solve that, you must have the ability to calculate the inverse kinematics of the robot. The forward kinematics, however, are also useful. For example, if you want to calculate if a pass is safe for the robot, if it will collide with an obstacle or not, then you need to know the forward kinematics. Let me just close a couple of frames here. So now I will show you, not this. This is the midterm, one of the ones that I had. I just want to show you, I'll give it to you as a sample. One thing is you can click on here, which will, if you look at it like this, then now there's no answers. If you click on it, then it will show you the solutions to the problems. Also, you can make notes, you can enter them here. And when you write the midterm next Thursday, then once you have a solution, you can try and submit it. However, you need to enter your name and student ID, and then you can submit answers to it, and then they will go to the Discord bot. So I think this may be helpful. It will allow you to see sort of what questions I asked in some other exam. So next class will be Thursday at 6 p.m. will be the midterm. For 3 hours. So have a look at the sample problem, the sample midterm that I just posted, and hopefully that will give you a good idea for the kind of questions that I will ask you. In principle, the problem, also the exam, is open book and open internet, so you can use Google, you can use internet connectivity, but what you're not allowed to do is communicate your answers and your questions with your fellow students. So it must be your own work. In order to receive full marks, show your answer. So if, for example, here, this question here, if the answer is 1219, but you don't show any intermediate results, how you got that answer, then you will not get any marks for the question. Also, when you submit it, you can include graphics from your program. So if you plot here, you can see you can upload an image. So if I ask you to draw something like this, Then write your program, save the image and upload it to your exam. And that's it. So are there any questions about the midterm exam on Thursday? No? Okay, good. Then go through the Jupyter notebooks that I covered in class. I won't ask you anything that I have not covered in class. And then I'll see you all next Thursday. Okay, so bye-bye. Finally, you can get some sleep or go out and have fun.